Hello there, our wonderful and esteemed viewers on this favorite mathematics YouTube channel, Mathematics by Abozena. That special channel I created for you and I to come together to demystify mathematics and tackle the age-long phobia associated with this all-important subject, one topic at a time. Today's class promises to be very interesting. We wish to appreciate you for continuing to stay tuned to us. Thanks and God bless. In the last videos, we looked at the concept of binomial distribution as an example of discrete probability distribution. We looked at conditions that will be met for us to name a random variable to have a binomial distribution. I'm taking two different classes of example on that topic, which I believe we found quite useful and impactful. Today, we take it a level higher again by looking at the other example of discrete probability distribution, and that is Poisson distribution. The Poisson distribution has the probability function given as probability of x equals to x equals to lambda raised to power x e raised to power minus lambda over x factorial, where x can assume values from 0, 1, 2, 3, and so on and so forth. The question then arises, when do we use Poisson? Poisson basically is used when you have a very large number, a large n. That's when we use Poisson. It might not be desired to use binomial when you have numbers as high as 10, 20, 30. So that's exactly when we are going to use Poisson. Then we need to know what sort of these parameters are. X is known directly as the values of respective occurrences from 0 and so on and so forth. The lambda is given as the product of n and the p, which should be in the question anyway. And e, the Euler's constant, is approximately 2.718. These two are the parameters we need for a Poisson distribution. So let's look at a classic example. In a large consignment, 7% of the items are defective. That's interest, defective. If a random sample of 50 items are selected from the consignment, find the probability that at least 4 will be defective. Okay, here we go. So to start with, we list n is 50 in this case. It is quite large. We can't possibly use this for binomial. Hence, we are opting for Poisson. Then here, what's our p? P is 7%, and that translates to 0.07. That's 7%. So after having gotten our n and p, we can then see our lambda is np, and that is 50 times 0.07. So our lambda is actually 3.5. So the state is set to now compute the probability required in the question. Now, coming to the question, we are asked to find the probability that at least 4 will be defective. And when you use the word or expression at least, it means that's the minimum. So if we say at least 4, that means 4 and above. And what does that interpret to? The maximum here is 50, so meaning from 4 up to 50. We cannot reasonably calculate probability of lambda of our x being 4, 5, 6, 7, 8, 9, 10, up to 50. That doesn't make sense really. Rather, we're going to see probability of x, which is greater than or equals to 4, that's at least 4, simply translates to 1 minus, we take probability of x equals 0, 1, 2, and 3 away from 1. Using again the concept of probability of sample space being 1. So that means probability from x equals to 0 to x equals to 50, everything will sum up to 1. So in other words, once we have known 0, 1, 2, 3, we simply add up and take away from 1. Then the resulting answer will indeed give us the solution desired, which is from 4 to 50. So the challenge now is how to compute probability of 0, 1, 2, and 3. And that isn't really much of a challenge. We go thus to compute. So we have probability of x equals to 0. To start with, that's the very first one. Using the formula, lambda is 3.5, x is 0 here, e is 2.718. If you're using your computer or your device, you can simply have that e there, use power minus 3.5 over 0 factorial is 1. So when you compute this, you're going to have 0.030197. That will be probability for x equals to 0. Similarly, when you have x equals to 1, that is 3.5 raised power 1, e raised power minus 3.5 over 1 factorial, which is still 1 in this case as well. Again, when you punch in the values in your device, you're going to have 0.10569. That will be pretty much that. Then we move on to when x equals to 2 to the third value there. We have 3.5 still, raised power 2, e raised power minus 3.5 over 2 factorial is still 2. That's 2 times 1. So when you compute this, you're going to have 0.18496. And the last one there is going to be 3. That is when x is equal to 3. So when x is equal to 3, that gives us 3.5 still, the power of 3, exponent minus 3.5 over 3 factorial. 3 factorial is actually 6. So when you compute this divided by 6, you're going to have 0.215783. Yes. So you've computed x equals 0, 1, 2, 3. The next thing we need to do now is to sum up. And sum up, remember, we're going to take it from 1. So we sum up this, we're going to have 0.53663. That will be the sum of that. To recall that probability that x is greater than or equal to 4, that's at least 4, is actually 1 minus probability of x 0, 1, 2, 3, which is 1 minus 0.53663. So when you compute this, you're going to have 0.46337 as the final value for probability of having at least 4 defectives from the consignment of 50. And that exactly is how the Poisson distribution pans out. Okay, completely different from binomial distribution. Once again, the Poisson distribution is given with the probability function lambda to the power of x exponent minus lambda over x factorial. X assuming values from 0, 1, 2, 3 up to the largest value possible for that question. And we said that the exponent for Euler's constant is given approximately as 2.718, and lambda is actually the product of n and the given probability in the question. And with that, we've come to the end of our Poisson distribution, which I believe you found quite interesting and fun as well. Thanks for staying tuned, and God bless. See you in the next video.